Hello, everybody. This is one of our required sections. We have to talk about graphs and the derivative. First, I want to make sure that we're very clear on what we mean by certain rules about graphs. So, if let's just get everything on the record. So, we're going to talk about what evaluating an x value in a function or its derivative tells us about the idea. So, if f of x is greater than 0, then the graph, apologies, that was my phone going off, and the graph is above the x-axis. Whereas if f of x is below 0, then the graph is below the x-axis. Okay? And this is using just the original f. Now, let's talk about what the derivative tells us. So if f of prime of x is greater than 0, the graph is increasing. That's a positive slope. And if f prime of x is less than 0, the graph is decreasing. Now, we're going to introduce the concept of a second derivative. And once again, we're interested in whether or not this second derivative evaluates to a number that is positive or negative. And we call this being concave up or concave down. Okay, so let's take a look at some prototypical graphs. And this is usually what I like to do. So these are all going to be our increasing versus our decreasing. And these are going to be our concave up and concave down. So there's these four sort of pieces. Okay, now what does it mean to be increasing concave up? Well, if you're increasing, that means from left to right, you're gaining in height. But if you're concave up, it means you sort of create this swell, and there's lots of ways to think about it. You can say it's turning to the left or it's curling upwards. I like to think about, imagine if rain were coming down. In a concave up scenario, that water would pool at the bottom of the concavity, right? The bottom of the valley, you might say. Versus, we could still increase, getting larger as we go from left to right, but if we increase like this, if we got rained on, well, that water would slip off, right? And there would be no pooling. This is the roof sort of idea. Now, if we're decreasing, the opposite is happening. From left to right, we're going to a lower position. But if we're decreasing concave up again, we're taking on water. And that water would pool at the bottom. Versus we could also decrease in a concave down sort of method, where that water would sort of slide off. So that's how I like to think about it. The important thing is that by stitching these pieces together, we can sort of determine what a graph looks like with some very, very accurate. Okay? So what do I mean like this? Well, let's take a function. So let's say f of negative 2 equals 3, f of negative 2 equals 4, and f double prime of negative 2 equals negative 1. Okay? So what do we know about this point? Okay? I know that at negative 2, I know it comes out to be 4. This just tells me the location. From the first derivative, I can see that the graph is increasing. So I'm expecting it to do something from left to right. But it's increasing concave down because the second derivative is negative. So increasing concave down looks like this one right here. I would expect maybe something like this is going on. And so I already get a really good idea about what's happening at the graph just based on derivatives. And that's sort of what we're looking at. What's the relationship between a function's derivative and its graph? Okay, so I'm going to take this one from your textbook. A question like this, I need to be very clear. A question like this will appear on the final, so I want to make sure that you're prepared for it. So it's telling us that f prime is less than 0 on negative infinity to negative 6. It says f double prime is less than 0 on negative infinity to negative 6. So we're just listing out some ideas. It says f prime is greater than 0 on negative 6 to negative 5. F prime, apologies. F double prime is greater than 0 on negative 6 to negative 5. F prime greater than 0 on negative 5 to 3. F double prime greater than 0 on negative 5 to 3. Going some more, we have f prime greater than 0 on 3 to 5. F double prime less than 0 on 3 to 5. And f prime greater than 0 on 5 to infinity, as well as f double prime greater than 0 on 5 to infinity. Okay, this is just a list of rules, but what we want to point out is that we can kind of condense these down. So we are decreasing concave down on this integral. And remember, what does it look like to decrease concave down? We're decreasing, and we're also shedding water. So I know the graph is going to look a little like that. Once we get to this point, we are on negative 6 to negative 5. We are increasing concave up. So what does that look like? Increasing concave up. On this point, we are increasing concave up again. Wonder why that... Oh, I apologize. I actually misread this. This one should be decreasing concave up. So if we're decreasing concave up, and that's just, I didn't read the right one. So we're decreasing, but now we're concave up. Remember, we're going to hold water. We're increasing concave up. Boom, boom. Down here, we're increasing concave down. Kablam. And right here, we are increasing concave up. I can stitch all of these things together to create a somewhat interesting looking graph, right? I can get an idea of the sketch. So we start off decreasing concave down, and then suddenly we're flat, and then we come up. Actually, let me, I'm going to stitch these together a little bit better, just so you can see the idea of the sketch. So if we take a look at this graph, something interesting happens at negative 6. So from negative 6, we do something like that. What happens from negative 6 to negative 5? We do something like that. From negative 5 to 3, we do something like that. From 3 to 5, we do something like that. And from 5 to infinity, we do something like that. So what's my rough sketch of what this function looks like? I'm assuming it's going to go down, Come back up. And just like that, I have a fairly accurate sketch, just to kind of smooth this one out a little bit, of the function. Even though I don't know where it is, I get an idea of the behaviors. And I can see some ideas. Like, first of all, I think this is really looking like an absolute minimum. And again, I don't have access to the actual graph. All I have access to is all of this information right here. So I'm willing to say that this is a somewhat accurate graph. Where exactly is it? I can't say. I can't say exactly, what this point evaluates to. But I can get the general trend of a graph. As it turns out, the derivative is telling us information. And as long as you have these four pieces that you can kind of cut and paste, and you can figure out where they all go, we can, I think, really easily sort of get these sketches. So let's take a look at a function like, let's do a polynomial. I like this one because we can find the values of it. So we'll do first derivative and second derivative. So that'll be 3 plus 3x squared plus 4x minus 3. And that will, of course, be 6x plus 4. Okay, so what are we going to do with both of these derivatives? Well, with the first one, we're going to find the critical points, which we already know. We set f prime of x equal to 0. That's 3x squared plus 4x minus 3 equals 0. We can use the quadratic formula, negative b plus or minus the square root of b squared, 4 squared, minus 4 times a times c, all divided by 2a. We'll also get the negative. So I find as critical points, x is approximately, again, these are rounded answers, 0.535, and x is approximately negative 1.869, rounded to 3 decimal places. These are our critical points. Now, what about the second derivative? We can find what we sometimes refer to as inflection points, which is the same concept, f double prime of x, set it equal to 0. This is where the concavity changes. So 6x plus 4 equals 0. Solving that, I think x equals negative 4 over 6, or negative 2/3. That is an inflection point. Okay, so what do I do with this information? With the critical points, I'm going to do a number line. I'm going to put negative 1.869 there. I'm going to put 0.535 here. And I'm going to evaluate some number in the interval between them. So just to kind of choose easy numbers, I'll do negative 2, 0, and 1, right? And I'm going to plug those into f prime. So let me do that. Plugging that into my calculator, we get 3 times negative 2 squared plus 4 times negative 2 minus 3. I get 1, but the whole point is that I get it positive, which means we are increasing. Now, plugging in 0, I can do this in my head. We get negative 3, which is negative, which tells me the function is decreasing. And at 1, it'll be 3 plus 4 minus 3, which turns out to be 4, which turns out to be positive. So we're back to increasing. So I have my intervals of increasing, decreasing, and increasing. This function is increasing on negative infinity to negative 1.869 and 0.535 all the way up to infinity. And it's also decreasing on negative 1.869 to 0.535. So you can imagine a graph it's going to start increasing, then it's going to decrease, and then it's going to increase. You can kind of see that. Now, there is other ways to do this. You could increase concave up or increase concave down. You could decrease concave up or decrease concave down. You could increase concave up or increase concave down. I'm sorry, I got those backwards. The whole point is we don't have a good enough picture yet, but we're going to do the exact same thing we did with the critical points with our inflection point. Here's negative 2/3. We're going to plug these into the second derivative. So something larger than negative 2/3, I'll call it 0. Something less than negative 2/3, I'll call it negative 1. And again, we're plugging into we're plugging into the second derivative. This is 6 times negative 1 plus 4. I'm going to get negative, which means it's concave down. And if I plug in 0, I get 4 positive, which means it's telling me concave up. So it's concave up on negative 2/3 to infinity, and it's concave down on negative infinity to negative 2/3. Okay, with all of this information, I'm ready to make my sketch. Okay, now I'm ready to graph what I think f of x is going to be. So we're going to start off, we're going to put all of the points together. So the first one is going to be negative 1.869. Then we're going to hit negative 2/3. We're going to put all our critical points and all our inflection points on the same graph. And here's 0.535. So below, I'm going to write the results of my concavity. So remember, we were concave down from negative infinity to negative 2/3. And then suddenly, we're going to be concave up from 2/3 to infinity. Doing from the first derivative test, we're going to be increasing, followed by decreasing, followed by increasing. Okay, now I just have to put in the behaviors. So, first section, from negative infinity to negative 1.869, I'm increasing concave down. What does that look like? Well, maybe it looks something like that. Now, I'm going to go from increasing to decreasing, still concave down, until I get to negative 2/3. Now, I'm going to keep decreasing, but I'm going to decrease with my concavity instead up, and you can see that inflection point right there, until finally, still concave up, I'm going to start increasing. And wouldn't you know it, there is my graph. Let me connect it all together. There's my graph of what I think this cubic function looks like. Now, do I actually have the right y-axis? The y-axis, it's just sort of a guess. We don't really have, we could go further, but again, this is a sketch, this is a macro view, we're just trying to figure out what we know and what we can identify. And look, something we can identify clearly, hopefully, obviously, here's a relative max, and here's a relative min. And we get that for free by doing these. What we just did in the blue and the red are sometimes referred to as the first derivative test, or sometimes called the critical point test. And what we did down here with the second derivative is, you guessed it, the second derivative test, also called the concavity test or the inflection test. So, listen, graphs and derivatives are not so far. Derivatives have this physical interpretation. We don't want to forget about that. Hopefully this video helps you on the homework, and I'll see you all in the next one.